And our next speaker is Christoforos Mavrogiannis.
Thank
Did you
you.
get it?
Yeah. Hello, everyone. This is joint work with my advisor, Reshape. So, as we all know, humans are quite good in navigating busy streets, crowded malls, or even narrow academic hallways, despite the lack of formal rules guiding traffic or the lack of explicit communication among agents. However, the same does not apply for robots that are still struggling integrating seamlessly in human environments. In fact, their motion can be hard to read, and this results in hindering or even blocking human paths. So what exactly goes wrong? What went wrong in the examples in the videos? Let's try to simplify the problem by looking at an abstract version of it. Imagine that we have this hallway, we have a robot, and we have a human, and they're both aiming at reaching opposing sides of this hallway. So as you can imagine, there are two main successful strategies to do so. There's the right strategy and there's the left strategy. However, in the examples that you saw, it was unclear which one of those strategies was going to emerge because the behavior of the robot wasn't expressive enough to allow the human to understand. And this diagram basically represents the belief of the human regarding the emerging strategy that the agents would follow to resolve the collision. And so, as you can see, this is a high entropy distribution. But humans are quite good in doing so. So how do humans reduce entropy? We took a look at studies on human behavior, and we found that the key turns out to be trust. Humans trust that others will behave competently. And this is illustrated in the pedestrian bargain by Wolfinger. This is not enough, though. Humans also implicitly communicate. They don't explicitly communicate, they don't exchange their trajectories, but they encode intentions into their motion. And so central to that is the concept of teleological reasoning by Xibra and Gergely, which basically says that humans tend to interpret actions as goal-directed in a given context. Okay, so in this work, we're contributing a topological model of cooperative navigation, employing the concept of the pedestrian bargaining, and a planning framework for accelerating consensus on avoidance strategies in a multi-agent context. Okay, so let's go back to the motivating example that I showed. We have this scene where those two strategies could be possible. Those strategies have a name. It's either the left strategy or the right strategy. But what does that really mean? What does the right or left mean? Well, from our perspective, left and right denote distinct classes of topologically equivalent navigation strategies of avoidance. And in fact, as long as the agents agree on the kind of strategy that they're going to follow, it's not even really important what sequence of coordinates each one of those are going to follow. Because since the human counterpart can't be trusted that is going to fine-tune the details of the trajectory to avoid collisions. Okay, but how do we generalize this to any number of agents? To do so, in this work, we employ the concept of braids from topology. To give you an intuitive idea of what braids are, consider a set of particles from 1 through n, and take those particles and imagine that you arrange those along the x-axis, with each particle being placed at its corresponding x-coordinate. So this arrangement corresponds to a permutation, P0. Now imagine that you want to start from this permutation and reach a final permutation by physically reconfiguring all those particles. The end result, if you think about the trajectories that could emerge in space-time, would look something like that. So these are the trajectories that the particles followed to reach their final destinations. And this pattern actually corresponds to a braid on n strands, where strands denote each strand corresponds to a different trajectory. Okay, let's take a closer look at what braids actually are. Braids, the set of all braids on n strands, along with a composition operation, form a group Bn. And this group can be generated by a set of n-1 elementary braids that are called the generators of this group. You can see the generators depicted in this graph, and the generators actually have to follow these relations. To get an idea of what composition means, look at this example. Sigma 1 can be synthesized with, for example, sigma 2 to the minus 1. Note that the minus 1 means that it's the inverse element, so the swap, the exchange that takes place in the inverse way than sigma 2, for example. And the resulting pattern is what you see to the right, and the pattern actually has a name. It's the product of its components, and this is called the braid word. Okay, so in this work, we make use of this concept to label and to refer to topological strategies of avoidance. So imagine that you have a scene, a workspace with multiple agents navigating, and think about their trajectories plotted in space-time. You would then get a pattern that looks like that. Starting from this pattern, for us in this work represents the avoidance strategies that all of the agents engaged in to avoid each other throughout the course of the scene progression. So starting from this pattern, imagine that you project all of the trajectories onto a selected plane, let's say the xt plane. And then imagine that you label those crossings by using elementary braids, generators. This way, you can extract a braid, which can be represented by its corresponding braid diagram, or the word that you see at the bottom. So the key idea here is that this braid is topologically equivalent to the strategy that the agents followed to avoid each other throughout the scene. This braid represents an equivalence class of topologically equivalent strategies of avoidance. Okay, so in the example earlier, we said that there was uncertainty with respect to the emerging avoidance strategies, and maybe the agents had conflicting ideas about the strategy that was going to emerge. So our goal here in this work is to build an algorithm, design a policy that would allow the agents making use of the concept of braids to converge to the same strategy of avoidance. How do we do that? We were inspired by the work of Dragan and Srinivasa on integrating inferences into the robot's decision-making. And how do we do so? Our goal by using that is to reshape the observer's belief from a high entropy distribution to a low entropy distribution through the action of the robot. And in this work, we do so by following this utility function. So the robot makes decisions by maximizing this function, which is composed by a term which we call efficiency, and it's basically the distance to the destination. But also, more importantly, it has a term that quantifies the consensus. It quantifies the status of the consensus regarding the strategy of avoidance among the agents. And the role of that is played by the entropy of a distribution over strategies of avoidance, given observation of past trajectories, given the context, and given the action in consideration. Okay, but the braid group for n higher than 2 is infinite. So infinitely many different strategies of avoidance could be mathematically possible. How do we conclude to a subset of relevant ones? Consider this workspace with those agents, and let's say that we somehow know that they're going to reach this final state. How do they do that? They follow those paths. But from the perspective of a planning agent, let's say that the red agent is the planning agent here. The initial arrangement of the agents corresponds to a permutation if we get the projections of all of the agents along the line aligned with the green axis, which represent the y-axis of the robot's local frame. And the red agent does the same thing for the final state. So the red agent is thinking that in the end, there's going to be this final permutation. So in the red agent's mind, there is a braid that takes all of the agents from their initial arrangement to a final arrangement. So how can the red agent then decide on this subset of relevant strategies? In this work, we do so by using this graph. This graph is called the permutohedron of order 4. It's composed of nodes, each of which corresponds to a different permutation of the agents. So in this example, the agents want to reach a final permutation PF from an initial permutation P0. So we search this graph. For example, we got 3 paths, and each transition can be implemented with braids by using an elementary pattern, so either a positive or a negative generator. So this way, we can conclude to a set of avoidance strategies S. And in this work, we consider a game setup to evaluate this strategy. Imagine that you have a set of agents that play a game. The game is played in rounds. At each round, each agent picks an action which corresponds to a neighboring square. Each agent is aiming at reaching the destination, and they want to avoid collisions. So the agents select actions simultaneously, and they are assumed to have full access to the state history and the destinations of other agents. So we compared a greedy strategy where all of the agents are greedily aiming at reaching the destination, so making maximal progress at each round, with our strategy, so a set of social agents that are thinking about how everyone would get to their destinations. And as you could see, our strategy leads to suboptimal choices that favor the social welfare in a sense, because everyone's decision-making gets simplified, as can be seen in this diagram of the mean entropy with the rounds. So there's a rapid decrease in the uncertainty for all agents that corresponds to a facilitation of the decision-making of everyone. Okay, so my dirty laundry slide. In this work, we used a very simple model of agents' belief. But we plan on using an elephant to learning a very good model of that. So in this also, another thing is the trade-off between efficiency and consensus. Although we didn't observe any high sensitivity on that, we would like to learn a better way to decide on that. We considered a simplified application setting, and we would like to consider more realistic ones, because our end goal is to apply this work on an actual robot moving around humans. And finally, another important question is how to determine the projection plane for each agent. And with that, I will leave this slide here, and I will take questions. Thank you.
Thank you. Questions?
Yeah, very interesting work. Thank you very much. One question I have is, what are your thoughts around scaling the number of agents? What's kind of the scaling behavior, and what strategies do you have in mind to scale to maybe hundreds of agents?
This is a great question, because obviously with the number of agents, it gets much harder to plan on the graph. I think to that we have a practical perspective. Since we're going to employ it on a real robot navigating around hallways, and we're going to have a limited sensing anyway, we're going to have a limited radius of consideration, because it doesn't matter if you are 100 meters away, maybe you won't be able to sense it anyway, but if you are very far, it's not very important right now to consider you in my plan. So that's our perspective on that.
Okay.